So in the derivation that we just did in the Intro to Gauss's law, we saw that when we considered a Gaussian sphere surrounding our point charge, that the radius actually cancels. So we get a very simple equation for flux that no longer depends on radius. And what that means is we could choose this big sphere, which has a big radius, or we could choose a little sphere that in fact has a smaller radius, and the flux is actually the same in both cases because you have the same Q. Now, this is important. You have to understand what these words mean. Is the electric field the same at this point and that point? No. If you just look at the field line diagram here, you see that the field lines are more greatly spaced, right? They're further apart, further out. And so your electric field out here is actually small compared to the electric field closer in. So even though we would say the flux is the same, that is not the same as saying the electric field is the same. So it will take some practice for you to know what these words mean. But we see here that in fact, the electric flux in this situation does not depend on radius. So this is actually going to lead us down a pretty interesting direction of analysis. What if instead of using a sphere, which is originally what we did, and we justified that by saying, hey, there's a good symmetry for it. Remember that your Gaussian surface really can be whatever you want it to be. So you can choose something different, and the math will just be disgusting, but you could choose it different. Now here I'm calling it a circle because we keep doing a side view, but of course before it was a sphere, and now we can imagine it being some sort of complicated ellipsoid. So I'll keep talking about the shapes in the two-dimensional way, but remember that these are inherently three-dimensional shapes. So let's try to simplify this ellipsoid into some radial and some circular pieces. So when I see radial, what I mean is pointing out from the center. So this would be a radial piece here. And circular, or like a little bit of a sphere, would be a piece like this. So you can see that this isn't giving me exactly my ellipsoid, but as long as I thought about kind of doing that calculus approach of making these little pieces smaller and smaller and smaller, eventually I would get there. Now everywhere that I have a radial piece, my flux is going to be 0. Why is that? Well, I know that my field points out this way. And so anyway, like here, in fact, no flux is pointing through my surface. That's why we were talking about parallel and perpendicular surfaces. So all of the radial pieces do not contribute to flux. But then you have all of your different circular pieces. And so your different circular pieces, in fact, do contribute to flux, but what we've seen is that the radius cancels out. And so this interesting thing happens here where we basically go, oh, actually, my flux calculation for this really complicated shape here, my flux is still going to be Q over epsilon naught, because all of these pieces are going to add up to basically give me Q over epsilon naught, and the red pieces don't contribute. So I am skipping a few of the steps here, but the important thing to notice is that our flux doesn't actually depend on the shape that we have put around our object, where that means, for instance, in the case of a sphere, spheres of different radius have the same flux. Here we've moved away from a sphere, but we see you actually get the same flux. So there are some more mathematical calculations you can do to test this, but typically we still have to choose simpler shapes so that the math is doable, but this is in fact going to be true for any shape. So for any Gaussian surface around a point charge Q, and again we're still not quite to Gauss's law because we're only talking about a point charge Q, your flux, which is defined to be this, right, that's how it's defined, is just going to be equal to the Q over epsilon naught. So again, this is easiest to directly calculate and to prove if you have a sphere, and for any other shape we can basically argue that it's going to be the same by approximating any other closed surface as a series of radial pieces and spherical pieces. So we now see that flux doesn't actually depend on what the Gaussian surface is, but for most of our calculations it will matter what we choose our Gaussian surface to be simply so that we can do the math. So we're not to Gauss's law. We need to generalize to all charge distributions, but we're almost there.